Welcome back, everybody. I still owe you an explanation of, the second part of the lecture slides on subgame perfect equilibrium and perfect Bayesian equilibrium, which is the part on perfect Bayesian equilibrium. So let's go through that step by step. The definition is a bit you could say cumbersome, but I think the best way to get a feeling of what perfect Bayesian equilibrium does is by simply looking at lots of examples. So we will briefly guide you through the definitions, but after that, I think the best thing to do is to simply see how that works in specific games. So maybe one thing to realize very well is that a perfect Bayesian equilibrium consists of two ingredients, a sigma and a beta. The sigma indicates what we already know, namely the strategy profile in the game tree. So simply the profile of strategies for all the players. And players are now allowed to mix, meaning that they are allowed to choose strategies with a certain probability or actions with a certain probability. And the beta is the belief, and that is, well, it sounds very religious, but basically what the belief is a probability assignment to the nodes within the information sets. So sigma is a profile of mixed behavioral strategies, and beta is a probability distribution over information sets, or per information set, a probability distribution. So, bit of terminology, like I said, so the beta is called belief, and the combination of a behavioral strategy with a belief is called an assessment. And of such an object, an assessment, we can decide whether it is a perfect Bayesian equilibrium or not. And in order for it to be a PBE, we need essentially two conditions. The first one is this one over here. So given the belief, given the strategy, the belief has to be what's called consistent with Bayesian updating, meaning that the belief is then formed by simply using Bayes rule. I'll see how that works in further examples. And secondly, given the belief, the strategy profile should be in such a way that for each player it maximizes its expected payoffs at each information set. So you have a probability distribution that says with what probability do you think you are in which node. And if you have such probabilities, then you can use the strategies for the other players to compute expected payoffs for your actions from that moment onwards. And the strategy assigned to you by the sigma should then maximize your expected payoff. That's a lot of words, but you'll see how it works in examples. A few short remarks. First of all, this first requirement on Bayesian updating is traditionally called consistency, written by cons. That's how it's called, but I always find it's not very informative term. So I always prefer to use Bayesian updating, because that at least tells you what you actually have to do if you want to check consistency. You have to check Bayesian updating, or use Bayesian updating. The second requirement is called sequential rationality, meaning that you should not only be rational at the start of the game, which mainly means that you have to play a Nash equilibrium, but you do that sequentially in the sense that you have to be rational in every information set, just like subgame perfect equilibrium requires you to be rational in every decision node and see what happens onwards. So in some sense, the sequential rationality is indeed, you could say, an attempt to use the notion of backwards induction in situations where the information sets are not singleton. Yeah, so another remark is that this Bayesian updating can only be applied in information sets with probability strictly larger than 0. And further, PBE is, yeah, so that's an assessment, right? The beta and sigma and the beta. But sometimes the sigma itself, so simply the strategies are called PBE as well, without mentioning the beta. But formally, you have to report both the beta, the sigma and the beta. Okay, so let's see how that works. Here is an example of an, well, this was a subgame perfect equilibrium from the previous recording. But this is not a PBE. We already saw that on the left-hand side, player 2 was doing something peculiar, right, in this part of the game tree over here. So this is a subgame. And we already decided that choosing left in this subgame is a peculiar thing to do. And now we can actually formalize that. Namely, here is the belief. So this alpha 1 minus alpha is the belief. In this game, there is only one non-singleton information set. So that is the only place where you need to form a belief. So all these other nodes, so for example here, yeah, you know that you have to be there with probability 1 because there's no place else to be once you are in this subgame. So, so that is easy. But in non-singleton ones, there you cannot apply this kind of, you could say, maximizing expected profits directly. So you have to have a probability distribution over these nodes. You have to say with what probability do I think I am in this node, and with what probability do I think I'm in that node. And once you have specified those numbers, so that's the alpha and the 1 minus alpha, you can compute expected payoffs. For example, just to give you an idea of how that then works. If this is your belief, so you think that you are in the left node over here with probability alpha, and you think with probability 1 minus alpha, I am in that node, then what is your expected payoff if you choose L? Well, with probability alpha, you are over here. And then you would move over there and your payoff would be 0. And with probability 1 minus alpha, you would be here, and then we move over there, and then your payoff, your player 2, right, would well, also be 0. And that's 0. And the same you can do for right. With probability alpha, you are on the left-hand side. And if you choose right, you get 1. And with probability 1 minus alpha, you also get 1. And that is then 1. So given that belief, the best action to take is to choose R. Yeah, of course, that's not very surprising because the payoffs are, you could say, constant, whether you are in one node or the other. But you could, of course, imagine that you could do the same if the payoffs would be 5 over here and 2 over here. And let's say 3 over here and 7 over there. Let me do that just to show you how it would look like in this case. If you would choose left, then with probability alpha, you get 5. And with probability 1 minus alpha, you would get 2. So that would be 2 plus 3 times alpha. And you can do a similar calculation for choice over right, which would give you 3 alpha plus 7 times 1 minus alpha, which is a net profit of 7 minus 4 times alpha. And now you could say, well, I prefer right over left, precisely in case 7 minus 4 times alpha exceeds 2 plus 3 alpha, which is saying that alpha should be maximally 5 divided by 7, if I'm not mistaken. So that's how it works. Yeah. Of course, in the case that we are actually facing currently, it's a lot easier because right is always better than left for any choice of alpha. But you can see that also in more complicated cases, you can actually apply this kind of sequential rationality. Anyway, the conclusion is that this is not a PBE because for any alpha, you have to choose R, and that is currently not what you're doing in this subgame. What would now be subgame perfect equilibria? Sorry, perfect Bayesian equilibria. Well, maybe that's a good thing to do. Let me go back one step. Well, maybe a good thing to remark is that subgame perfection is implied by perfect Bayesian equilibrium. So if you would apply perfect Bayesian equilibrium to these singleton nodes, then you get exactly subgame perfection. So any PBE is at least an SPE. So we already know that for the SPE here we had to choose C, and here B, and then here we chose L, right? But now, because of the introduction of this belief system over here, we also know that player 2 has to choose R in this information set. So we also always chooses R, B, C. And then what should player 1 do? Well, if he chooses B, he gets 8. If he chooses C, he gets 8. And if he chooses A, he gets 1. So for sure, he's not going to choose A. So he can choose either B or C. So we can choose any combination thereof. And then should he choose 1 or 2? Well, if he chooses 2, then we go here and we go there, and he gets a payoff of 6. While if he chooses 1, then either he chooses B or C, and in both cases he gets 8. So for sure he's going to choose 1. And alpha can be anything as well, right? So the belief system, well, can be anything, but it's given by this choice over here. And you should make that a bit clearer. So we saw now that the strategy for player 1 would be this, but now you can also compute the alpha. The alpha is now given by consistency. So what does consistency say? Well, we have that the game goes over here with probability 1, and then with probability lambda we go over here, with probability 1 minus lambda we go over here. So if you would apply Bayesian rule, right? What would you get? You would get alpha is lambda, the probability to be in this node, right? This lambda, divided by the total probability to be in this information set, which is, basically 1 plus lambda plus 1. Oh. Lambda plus 1 minus lambda, which is lambda. So any alpha is possible, but it is dictated by the probability that player 1 is using for his choice of B or C. And also here, of course, in this case, this is easy, but also if this would be a probability that is less than 1, you can still apply Bayes' rule. The only exception is when this would be exactly 0. And in that case, you cannot apply Bayesian updating. And that means that in that case, you can say that you can choose any alpha as long as sequential rationality is respected. We'll do that in the next recording. So, see you there.